Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. We've got a great panel today to really dig into where we are with AI and where we're headed.
Yeah, excited to be here. It's a fascinating time to be working in this field, isn't it? Feels like things are moving faster than ever.
Absolutely, though I'd argue that faster doesn't necessarily mean we're on the right track. We need a more nuanced perspective, I think.
I agree that speed isn't everything. We need to be smart about how we go about it. It's like, are we really building something intelligent or just sophisticated pattern matchers? That's always in the back of my head.
Right, and that's exactly what I find so compelling about combining neuroscience with AI. I mean, we have this incredible model of intelligence already built into our brains. Why wouldn't we try to understand its underlying mechanisms and then translate that into our machine learning algorithms? We're sort of just stumbling around in the dark otherwise.
Well, I think deep learning has shown that we don't necessarily need to copy the brain, necessarily. I mean, look at the progress we've made just in the last few years. Models are now generating incredibly realistic images, writing coherent text, translating languages, even beating humans at complex games. All of this without a detailed biological blueprint. It suggests we're on the path, and more data, bigger models, and clever architectures are the key.
See, that's where we fundamentally disagree. I see that progress as impressive, yes, but also incredibly brittle and ultimately superficial. Deep learning models are great at pattern recognition, but they lack true understanding. They don't reason, they don't extrapolate well beyond their training data, and they are easily fooled by adversarial examples. They're basically black boxes. I think we need to move towards neuro-symbolic approaches, integrating the best of connectionist and symbolic AI.
Yeah, and it's like these huge neural networks, they're working in this kind of static, time-agnostic way. They lack an intrinsic sense of space and time, and I suspect that this is crucial to true intelligence. I feel like we're using a brute force technique, like we're throwing more data, more computing power at the problem in hopes of the solution appearing. Instead, I think we need to be thinking about how biological brains process information in spatio-temporal context. The way information is transformed and translated between coordinate representations, like the transformation from retina to motor cortex, for example, that's the stuff that really excites me.
Exactly. And that's where, when I say combining neuroscience, it's not about directly copying the brain neuron by neuron. That's impractical. It's more about, for example, understanding the principles of hierarchical processing, predictive coding, the role of oscillations and synchrony, and then building AI systems based on those principles. For example, research by Jeff Hawkins and the Numenta team around cortical columns and their role in sequence learning is fascinating. If we could get a system that not only recognizes patterns but understands the underlying temporal structure, we could achieve a lot more than we are now.
But you know, the deep learning guys are also starting to integrate temporal processing with recurrent neural networks, RNNs, and transformers now. The transformer architecture has been huge for NLP. It's amazing how much context they can process with their attention mechanisms. The fact that you can model temporal dependencies within the system without any pre-wired notion of time is really powerful. It is a really big leap from simple feed-forward networks, and the scaling laws they hold to. The bigger the model, the better it performs. I think that's a sign that we're headed down the correct path.
Yes, transformers are a step forward, but they still operate on basically a flat data representation. They're still not understanding the underlying conceptual framework, or the spatial and causal relationships that are at the heart of human understanding. They struggle with common sense reasoning, like, you tell it a bird can fly, it assumes that all birds can fly. They struggle with counterfactual reasoning, what-if scenarios. Neuro-symbolic approaches by using an explicit symbolic layer alongside neural networks are much better at that, giving you a richer internal representation. Take, for example, how people think about objects. We have a detailed symbolic representation of objects, their attributes and spatial relationships that allows us to reason much more powerfully.
Right, and that explicit spatial and temporal modeling is absolutely key, the kind of thing that deep learning really lacks. For example, when I watch a ball being thrown, my visual system is working to predict where it's going. It's mapping that trajectory in a spatio-temporal way. That's not just pattern recognition, it's an active inference. The brain is using its own model of the world to predict the future, not just processing a static image, and that I think that's critical for genuine intelligence. Deep learning still struggles with dynamic environments and is slow to adapt to new scenarios.
I think that's such a great point, and it really highlights how the brain constantly makes predictions and adjusts its internal model based on incoming sensory information. Predictive coding, for example, says that our brain is actively anticipating what will happen next, and it's constantly updating its model. And when we encounter things that violate our expectations, it's those prediction errors that drive learning. That's where I see neuroscience can contribute so much to improve our AI models. We're still learning how the brain builds these internal models of the world, and we could implement these principles in a way that is similar to the brain. That to me seems like a much more promising route to AGI than brute force scaling.
But doesn't the prediction error framework essentially describe how neural networks already learn? I mean, backpropagation is essentially a mechanism for updating model weights based on the difference between predicted and actual outcomes. And yes, these internal models aren't explicit, they are embedded into the weights of the networks, but they are still there. Also, the models are getting so complex now that the emergent behavior is just amazing. If you ask me, the path is clear: more data, bigger models, novel architectures, and the emergent properties of these models will lead to AGI. It's just a matter of time.
Backpropagation is a crude learning mechanism. It requires labeled data, and it's incredibly inefficient compared to how humans learn. We learn from a very small number of examples, and we can generalize new concepts very easily. A neuro-symbolic approach might use neural networks for low-level perception, but then integrate this with symbolic reasoning modules. The symbolic component gives the model the ability to represent facts, rules, and make deductions about the world. This is much closer to how we understand and reason about the world. For example, you look at a robot moving around, and with one glance, you can grasp a detailed understanding of its trajectory, its purpose, its constraints, and this kind of rich abstraction is still missing from pure deep learning.
Exactly, and the spatial relationships are key, like understanding that an object is behind another or the trajectory of a moving object are fundamentally geometric and spatial problems. Deep learning deals with these spatially implicitly, whereas a neuro-symbolic system could encode this information explicitly using symbolic representations along with vector transformations. This explicit representation opens doors to better generalization, and we can't forget the temporal aspect too. These are all spatiotemporal dynamics that we need to capture in our models, and that's where I think coordinate transformations come in. Biological brains seem to have a core algorithm for doing this, translating the world into various coordinate systems, and that, I believe, is the key to true AI.
But I mean, aren't convolutional neural networks, CNNs, doing just that? They have these layers that extract features at different scales, from edges to patterns, to objects. And the latest transformer models can combine these spatial features into complex representations. We are making strides in building hierarchical representations, just in a different way to the brain. I still think that focusing too much on mimicking the brain's specific biological details is going to distract us. We should just keep pushing the boundaries of deep learning, increase the amount of data that compute, and refine the architectures. The power of the scaling laws are incredibly strong, and we are seeing results already.
But scaling alone won't get us to AGI. It may yield better pattern recognizers, but it won't give us true intelligence. CNNs still struggle with things that are trivial for humans. They require vast amounts of labeled data. They lack common sense reasoning. And these things, they're not simply a matter of increasing data or computing power. I mean, look at the work of Melanie Mitchell. Her work has demonstrated how brittle these systems can be when you deviate from the training dataset. Instead of thinking of deep learning as the all-encompassing answer, we should be exploring the advantages of symbolic AI. How can we combine the representation power of symbolic systems with the pattern matching of neural networks?
And I totally agree with that. I think we also need to change our thinking about representations too. It's not just about learning hierarchical features, it's also about how those features are represented internally. Take, for example, the human vestibular system. It allows us to perceive motion and orientation in 3D space. The information coming from the vestibular organs is processed and transformed into other coordinate systems in the brain, giving us a rich sense of body position and orientation. This kind of continuous spatial transformation is almost completely absent from current AI systems. That's why I think we need a new kind of core algorithm that allows the information to be translated between various coordinate systems and then will unlock a whole new area of intelligence.
And it's not just about perception, it's also about how we interact with the world, right? Embodiment is key to developing truly intelligent systems. The way that a robot interacts with the physical world and learns from experience, and that's really where the neuroscience principles become very applicable. Take, for example, the concept of active inference, which says that our brains generate predictions about the world and are constantly testing these predictions. And our actions are driven by those predictions and the drive to reduce the prediction error. I think that an active inference framework could be extremely helpful for training robots to interact with their environments in an efficient and adaptive way, rather than just training with passive data.
Yes, I agree that embodiment is a huge factor, and this is something we're seeing a lot of progress in, combining AI with robotics. However, we still can do a lot with simulated environments and virtual embodiment. Deep reinforcement learning agents can now learn to navigate complex 3D environments, solve puzzles, and perform intricate manipulations. I think that the focus should be on making these systems even more robust, training them on a variety of different environments so they can generalize to new conditions, and that this will give us a good path towards more general purpose AI.
But these reinforcement learning agents are very much a tabula rasa. They start from scratch, and they require vast amounts of experience to learn basic skills. If we could imbue them with some kind of innate knowledge and then allow them to learn, we can make the process far more efficient. That's where you start thinking about concepts and the kind of symbolic knowledge humans carry. Instead of just reinforcing actions that lead to a reward, you could have an agent that understands what it's doing and that uses symbolic reasoning to plan its actions and then a neural network to execute its plans. We'd get a much more general and flexible intelligence.
And that knowledge also needs to be spatio-temporally aware. Think about how we navigate. We build up a mental map of our environment with spatial relationships encoded, and we can then use that map to plan routes. This requires an ability to translate between different spatial coordinate systems, from egocentric relative to the body to allocentric independent of body. And again, that's why I keep coming back to that core algorithm for spatial transformations and how crucial it is. If we can model the brain's ability to map and navigate space and time, then we'd make huge leaps toward AGI.
So, if we want to really make a leap towards AGI, we need to not just build better models, but also better understand how intelligence actually works. And that means embracing the principles of neuroscience, like hierarchical processing, predictive coding, active inference, and embodiment. We need to move beyond simple pattern matching and develop systems that can build dynamic internal models of the world, using neuroscience as inspiration. We need to see neural networks not as black boxes, but as components in a bigger system that can process information efficiently and adaptively. I think we are making some progress, but we need to accelerate the work in neuroscience to fully understand the underlying principles.
I still believe that deep learning is the most promising path to AGI. It's the only approach we have that scales with data and that has given rise to such impressive emergent behavior. We don't need to recreate the brain's biology. We need to build systems that can learn to solve problems in a general way. I think we are on the right track with transformers, and further refinements in architectures, along with more data, will get us to AGI soon. I am very optimistic that we will see machines that can reason, understand, and learn just like humans using the deep learning approach.
I remain very skeptical. We need to move away from just blindly throwing data and computing power at the problem. Deep learning has plateaued in its capabilities, and we are getting diminishing returns. We need a new approach. We need to develop AI systems that are grounded in symbolic representations, that can reason and plan using logic, and that can build an understanding of the world using common sense. Neuro-symbolic architectures, combining the strengths of neural networks and symbolic reasoning, are crucial if we are to get anywhere near AG or GI. We need to stop trying to emulate intelligence. We need to build true intelligence.
And I feel the key to AGI is in that core spatio-temporal algorithm that the brain has, which allows it to create these flexible internal models of the world and then to translate this information between multiple coordinate systems. Deep learning, as we have it now, doesn't have that, and this is what limits its flexibility and adaptiveness. We need to be thinking about the brain's dynamic and continuous transformations and how to encode them in a computer algorithm. I strongly suspect that once we have that in place, we can start building AI systems that truly understand space, time, and all the rich information that the world provides, and that's when we will see true AGI.
So, looking ahead, if we each had a research direction to propose, from our perspectives, what would they be? I would propose research into the neural basis of predictive coding and active inference. Let's develop computational models based on these principles so we can build systems that can not only perceive the world, but also make predictions and adapt to new situations quickly and efficiently, the human way. We should move beyond supervised and reinforcement learning and move towards AI agents that have an intrinsic understanding of their environment. I think that's the key.
Okay, from my perspective, I'd say let's continue to push the boundaries of deep learning. We need to explore even bigger transformer models, train them on massive data sets of text, images, and videos. The goal is to see the emergent properties. Let's refine training techniques, make the models more robust, and reduce their bias. There is so much still to explore. We should also investigate the application of deep learning to more complex problems, especially in robotics and real-world scenarios. We need to see what these deep networks are capable of with more compute and data.
I think we need to refocus efforts into building neuro-symbolic architectures, ones that combine neural networks with symbolic reasoning modules, giving us rich internal representations that can reason and plan. We need to make sure these AI systems are not just pattern matchers, but actually understand the world. We need to imbue them with knowledge and make them able to reason and extrapolate that knowledge. So my research direction would be towards more symbolic-based AI approaches to create hybrid models that combine the strength of both paradigms.
And from my perspective, I think the big question is this. Can we develop a core algorithm for processing spatial and temporal data? One that has the ability to transform information between different coordinate systems like the brain does. The research should focus on discovering this algorithm, which might be something completely new, and then use this to build AI models that can build robust and flexible internal models of the world. This would be a complete departure from the status quo, moving away from the brute force scaling methods we see now. The future is in spatiotemporal, dynamic AI models.
That's a fantastic set of proposals, and it really highlights the diversity of research directions within this field. It's clear that there's no single answer to AGI and that we need to be exploring all these avenues. It's been an incredibly insightful conversation. Thank you both.
Yeah, absolutely. Really fascinating discussion. And it's great to hear all the different perspectives, even the ones I disagree with. It forces you to really think about the fundamentals.
I agree. It's good to have these different points of view. We won't get anywhere without having rigorous debates and being open to new ideas. It's always good to be challenged.
Yeah, I've really enjoyed it. It's great to have an open forum to discuss these ideas, especially when we have such varying opinions on how to get to AGI. It's clear we are making progress, just in different directions.